Welcome back, everyone. We're going to finish up our video series on summation and use of the summation symbol. And we're going to remind you what mean and variance are. And the main point of this lecture is both to either remind you or tell you about these concepts for the first time and to tie them back into sigma notation. It's one of the main uses of sigma notation. What I'm going to do here is scare you a little bit by showing you the punchline of the video at the beginning, but we'll walk through this very, very slowly and unpack it. So the whole point of the video, if you understand the screen, you've understood everything, is if we have a set of numbers x, which has n numbers in them, x1 to xn, these are just real numbers, the mean of that set, the symbol mu sub x, can be expressed as, in summation notation, this way. So this is the mean of x, sort of an average. And this ridiculous set of symbols here, this is called the variance of x. The point of the video is to understand what that is. And finally, by the way, was just plain old sigma, which is the square root of sigma squared. This is the standard deviation. And we'll walk through all that. Okay, now that we've seen that fancy sigma notation, let's work a really simple small example with numbers and then generalize. So suppose we have a set Z, which has three things in it. So here's 1, 5, and 12. And remember old notation, the cardinality of Z is 3, because there are 3 elements in Z. If we take the mean of Z, what that really means is we add up all the numbers, 1 plus 5 plus 12, and we divide by how many numbers we have, in this case 3. So if we do that, never a good idea to do arithmetic in public, obviously I've done this in advance, so that's 18 over 3, which is 6. That's the mean. And there's lots of notation for it. The most correct general notation might be the Greek symbol mu for mean, and we usually put a sub z down here to say it's, hey, it's that set Z we're using. Sometimes you'll see it's mu of z, as if it's the argument to a function. Often you'll just see mu, because we know what we're talking about already. Okay, that's a simple example with numbers. Let's do a slightly harder example with symbols instead. Suppose I give you a set y, which consists of 4 numbers, but I don't tell you what they are. y1, y2, y3, and y4. Then the mean of y, mu sub y, would just be 1/4 times y1 plus y2 plus y3 plus y4. And aha, here comes the punchline. Let's express this in sigma notation. This is 1/4 times the sum from I equals 1 to 4 of y sub I. Right, and that's really the mean. Remember, I is a dummy index. I could use j, I could use a smiley face, I really could use whatever I want. Let's not get too radical, let's use I. Okay, so we've generalized. Let's generalize a little bit further. In general, suppose we have a set x consisting of n arbitrary numbers. They exist, but I'm not going to tell you what they are. x1, x2, up to xn. The mean of x is, pretty easy to guess this now, mu sub x is equal to 1/n times the summation from I equals 1 to n of x sub I. That's the mean using sigma notation. By the way, it's worth thinking a little bit about the two different kind of philosophical functions of I and n. I is not a real variable, right? I is just a counter. It says, hey, count from 1 up to n. That's why we call it a dummy variable. Hey, you dummy, you're not doing anything except ticking the counter up from 1 to n. N really is a variable, right? N tells you when to stop. I'm not telling you what n is. If n is 10, you'd stop at 10. If n is 11, you'd stop at 11, and so on, right? In the previous example, we saw n was 4. Okay, before we jump into variance, I want to take a little sideline and tell you about something called mean centering. The reason I'm telling you about this is a common trick used throughout a lot of data science techniques. You'll see it later in linear regression, for example. Punchline here is if you have a set of numbers, you often want to change the set of numbers so that its mean is centered at 0. There's lots of reasons why. Let me just walk you through the mechanics of what it means to mean-centered data. No pun intended. Here's our friend Z. It has 3 elements in it, 1, 5, and 12. Previously computed that the mean of Z is 6. Over here we see the 3 elements in Z in blue, 1, 5, and 12, and there's the mean 6 there. Let's form a new set. Let's call it Z prime. What I'm going to do is to every element in Z, I'm going to subtract off the mean. So 1 minus 6, 5 minus 6, 12 minus 6. And oh dear, 3 examples of arithmetic in public. This is minus 5, this is minus 1, and this is 6. So there's z prime. Note, if I compute the mean of z prime, I'm going to get 0. This is minus 5 plus minus 1 plus 6 over 3, and that works out to be 0, unsurprisingly. What we're actually doing here, let's throw another copy of the number line, is we're saying, hey, you see that red dot there at 6? I'm going to pretend that's 0. How am I going to pretend it's 0? I'm going to yank it back over to 0, and I'm going to sort of be accountable for what I've done, so I'm going to shift everything over. So in other words, if you like, here's 0, 6 is going to 0. That's going to become a red dot. And then everyone comes along for the ride. So 1 has to go all the way to minus 5. 5 has to go to minus 1. Everyone's getting shifted the same amount. 12's got to get shifted over here to 6. And that's mean centering. The punchline is whenever you mean center data, you produce a new data set which sort of has the same relationships, but the mean is 0. There's lots of reasons why you want to do that, which we'll get into later. Alright, the last topic of today's video is a statistical concept called variance. I should mention, one of the points of a mean is when you have a large set of numbers, in this case large is 3, but large could be 3 million. Statisticians and data scientists often don't like a large amount of numbers and large amounts of information, so they want to summarize the set by a small set of numbers. So summarizing a set by its mean is about the simplest thing you can do, but it gives some information. What we're going to see here is an example of where it obviously doesn't give complete information. Here's a set Z, which is 1, 5, 12. We're getting bored with this. It's our friend. We get bored with our friends. Mu sub Z is 6. Fine. Here's another set W, 5, 6, 7. If we calculate mu sub W, it turns out that's also 6, so you can check for yourself. So obviously, it's not the case, unsurprisingly it's not the case, that the mean is not a unique classifier of a set. We have 2 sets with the same mean. Okay, let's look at these sets on the number line and see that obviously the mean's not telling the whole story. Here's 0. Here's the mean at 6. Let's draw a Z in blue. So here's 1. Here's 5. Here's 12. And let's draw W in yellow. So yellow actually has a dot right here on top, 5. There's a dot right there at 6, and a dot right there at 7. Okay, so they have the same mean, but if you had to say in a word what the difference is between yellow and blue, you might say spread out. Okay, that's 2 words, right? You might say that blue is more spread out than yellow. And there's a statistical, mathematical, data science concept called variance, which basically tells you how spread out data is. Let me just write that down for you in general, and then we'll compute it for these examples. So, if x is equal to x1 to xn, the variance of x is this. It's got this funny symbol called sigma squared of x. It's a Greek symbol sigma, we square it, and we put sub x to really denote that we care about x. This is 1 over n, and then this is going to look really intimidating, but it's not. We take the sum from I equals 1 to n. We look at xi. We ask how far is xi from the mean, xi minus mu sub x. We're going to square it. Talk about a little bit in a second why we want to square it. This is the variance. What this is really doing, let's look at the term inside the square. For every single xi minus mu sub x is really the question, how far are you from the mean? The reason we square it is we don't really care if you're to the right of the mean or the left of the mean. We just care how far are you. So for example, if xi was 1 and the mean was 6, that'd be a pretty big number. If xi was 5 and the mean was 6, that'd not be that particularly big a number. And then essentially what we're doing is we're taking the average of those numbers, right? Xi minus mu sub x squared, we're taking the mean of those numbers, which is why we're dividing by n. That's the idea of a variance. Something else you'll often see is if I take sigma sub x, which is just the square root of sigma squared, this is called the standard deviation. Okay, great. So let's calculate that for these two examples. Before we do it, though, we sort of should home cook it and know what the answer is, right? We know that z and w have the same mean. Z is more spread out than w. Somehow I'm trying to sell you on the idea, trying to get you to buy that the variance is a way of quantifying the notion of being spread out. So whatever sigma z is and sigma w is, sigma z better be much bigger than sigma w. Otherwise, this is junk. Okay, so let's close just with our example. Let's recall z is 1, 5, 12. W is 5, 6, 7. And the mean of z is 6, which turns out to be the mean of w, because that's how we cooked it. Let's start with the easy one. So sigma squared sub w is going to be, let's see, in this case, n is 3, so 1 over 3 times the sum from I equals 1 to 3 of, let's call this w1, w2, w3, and this over here is z1, z2, z3. The sum of wi minus mean of w squared is equal to 1/3. So now the first one, w1, is 5 minus 6 squared plus 6 minus 6 squared plus 7 minus 6 squared. And if we work that out, that turns out to be 1/3 times minus 1 squared plus 0 squared plus 1 squared, which turns out to be 2/3. Great, and so therefore the standard deviation, sigma sub w, is just the square root of 2/3. All right, if we do another calculation, if we do sigma squared z, this turns out to be 1/3 times 1 minus 6 squared plus 5 minus 6 squared plus 12 minus 6 squared. Now this is really not arithmetic I'm going to do in public, so I'll do a ... Last refuge of someone who doesn't want to do arithmetic. And this turns out to be equal to 62/3. Which I don't really care what that is. Punchline is I think that justifies saying much, much greater than 2/3. Which justifies our intuition that z and w have the same mean, but z is much more spread out than w, as measured by the variance.